Okay, my second video went longer than I wanted, so I want to do a third one, and I want to do this problem here, worksheet 6, 17 to 20, 400 ohms resistance, 500 ohms inductive reactance, 800 ohms capacitive reactance. In order to do this in LT Spice, you'd have to pick a frequency, figure out what inductance you had would give you 500 ohms at that frequency, figure out, pick a capacitor. Well, you got a frequency and then a capacitive reactance of 800 ohms, figure out what capacitance that would relate to if you wanted to do it in Spice, and that way you're working backwards. What I want you to see with this problem is the additive of the impedance. So if I go over 400, up 500, down 800, I am effectively going over 400 and down 300. And in my last video, I actually put that in there. I'm going over 400 and I'm going minus 300. So my impedance is 400 minus 300i, or 500 at an angle of minus 37. So that's my impedance. And if 250 volts is applied for that impedance, which I just calculated, what current would be expected? So I could take the 250 angle 0, divide it by the 500 angle minus 37, and I wind up with a current that is 0.5 at an angle of, I'm just going to make it positive 37. So this is my current, half an amp, 37 degrees, which breaks down into real 0.4, 0.3 to 2 decimal places. So that would be my current. What current would be expected at the multimeter? My multimeter would read a half an amp. What would my voltage drops be? Now this is the interesting thing. I got to take that current with that angle and multiply it times my resistance. So what I would wind up with is, here's my current, here's my angle, and if I multiply it times 400 angle 0, then a half an amp times 400 is half an amp times 400 is 200 at an angle of I add the angles, 37. So that's my voltage. And I want to change this polar into rectangular. So my voltage drop across my resistor will be 200 volts at an angle of 37 degrees. And this is what it is in rectangular. Now I ask for the voltage drop across the inductor. The inductor is 500 ohms. It's got a half an amp through it and 90 degrees. So if I go back to the spreadsheet, I've got 500 inductive reactance at a positive 90 degree angle, and my current is 0.5 times 500 gives me 250, and then my angle is 37 plus 90 because I'm multiplying it together, so that would be 127, and this would be my VL. So I can actually do that. This is my VR, if you will. Magnitude, angle. I'm going to take this polar form and I'm going to change it back into rectangular. I did the resistance one here. I'm going to do the polar one right below it. So it has a 250 with an angle of 127. Okay, so that is my VR. This is my VL. And so the last one will be my VC. And my VC is 800 at an angle of -90. So if I multiply that times a half an amp at 37, I'm going to wind up with magnitude of 400. And my angles would then subtract. So 37 minus 90 works out to be -53. So I'm going to go down here and I'm going to put that in as well. So I've got 400 and my angle is -53. The angle is about right to start with. Okay. So that is my total of my voltage drops. What I have applied is 250 at an angle of 0. Okay, so if I was to add these three voltage drops up, magnitude and angle, what I should get is 250 at an angle of 0, because that is my applied voltage. Kirchhoff's voltage law is always true. So what I did is I converted them to rectangular. And so what you notice here is if I was to add 120 and 199 positive and -319, I get about 0. So I get my 0, and I'll put this on the bottom as well. I get my 0 if I add these up. Matter of fact, I think I can just sum them. Let's see. Sum of, close the window down a little bit. Will it do it that way? No. Fine. If I sum those, I get 0.57. So let's put that 0.57. And if I sum these, which all I have to do is copy, Control C, Control V, I get 250.1. So from a rectangular standpoint, I get 250.01. And that works out to have a magnitude and angle of 250 at a angle of 0.13. Does that look familiar? And the reason I work this problem is if you're in an electrical circuit, you do have capacitance and reactance, you can actually see a voltage drop greater than what you've applied. So the one across my inductor is equal, the one across my capacitor is much bigger than what's applied, the one across my resistor is the same. And in an earlier circuit, the one for 11 through 14 or 11 through 13, whatever problem it was, we built a circuit and you can actually measure that and see it. But this problem amplifies it a little bit, 11 through 14. So you can sort of see that, and that's what happens in AC circuits. But Kirchhoff's voltage law is always maintained. And I wanted to go over this problem to let y'all know that. Anyway, I was running long in the last video and don't feel like I did it justice, so I wanted to add. Thank you for watching.